This question uses the concept of moment, and you are required to determine which of the three scenarios, pedal positions, will give the maximum moments or the maximum turning effect. Now, moment is affected by two things. As you know in the equation, moment is equals to force times perpendicular distance. In this case, the pedaling force is mentioned to be the same in these three scenarios. So we are looking at perpendicular distance. The scenario with the greatest perpendicular distance will get you your maximum turning effect or maximum moments. So that is the strategy that we will be using. Now, the answer to this question is B, because in position B, the perpendicular distance is the maximum. Okay. Now, I have put in the pivot point in yellow for the three scenarios, and if you look at option B, that's where the pedaling force is downwards, and I've marked out the perpendicular distance in blue for option B. It's worth noting that this perpendicular distance is more than the radius. If you look at the diagram carefully, the red color arrow, force arrow, is further outside compared to the radius of the wheel. Okay, so the perpendicular distance in option B is slightly more than the radius. Now we can analyze option A, and we noted that the force actually passes right through the pivot. This will give us a zero turning effect or zero moment. And for option C, the perpendicular distance is lesser. So I have marked out for option C the downward force again. And you notice that the perpendicular distance without calculation, you can already see that this perpendicular distance in blue for option C is smaller than the radius. So with this, without any calculation, you can already determine the answer to this question to be option B. Now we take this one step further, and we just need to use what we learned in math about Torcaso trigonometry to determine exactly what is the perpendicular distance value for option C. So I've enlarged option C in the slide, and I've just recreated the downward force, the pivot point, and our aim now is to determine the perpendicular distance value. And actually the answer is already written over here, L cosine theta. We will derive this in a while. It looks complicated, but it's actually not. It's just a simple application of Torcaso. So the base of this triangle, I hope you see a right angle triangle. So the base of this right angle triangle is the perpendicular distance, which we are looking out for. And if you look at the green color arrow, that line tells you about the length of the pedal. So I've put L as the length of the pedal. That is the hypotenuse of the triangle. And I put in an angle, and just let it be theta. So with this right angle triangle that you see, the perpendicular distance can be determined very easily. I challenge you to just write cosine theta. Cosine theta equals to something over something, which is Torcaso, the car in Torcaso, right? So it's adjacent over hypotenuse. So just write cosine theta and in a fraction form using Torcaso, and you will be able to get the perpendicular distance is L cosine theta. So this will come in handy if it's a SQ, a structured question that requires you to determine the exact length of this perpendicular distance for you to calculate your turning moments for scenario C.